Hello there, this is Wild Red, and I'm here today to talk to you about some of the things that contraction mappings and fixed point theory can do for you. Now, what exactly is a fixed point application? By that we mean we have a transform T, which takes in something and puts out something in exchange. So T of x equals y. So you can think of T as a kind of a little factory. You put x in, you get y out. You put in an orange, you get out an apple. You put in an apple, you get out a peach. Finally, you put in a kumquat and you get a kumquat. That's a fixed point. What can it do for you? Well, if you've ever been stuck on a mathematical problem where you don't know which way to turn, you've run out of ideas, this is one more idea to put in your bag of tricks, which will sometimes help. Let's start with an example, something you may have seen before. You're looking for the square root of p, and to get it, you take the equation x equals 1/2 the quantity x plus p over x and iterate. Namely, we're saying that t of x is the transform on the right hand side of that equation, and we're solving t of x equals x. But the way we solve it is iteratively. The next slide shows that iterative process. It shows we start with a guess of, in this case, 10 as our first guess for what the square root of 2 turns out to be. Then we take the transform and apply it. First time we apply, we stick in 10 for x, do the computation for t of x, and we find that the output is 5.1. Then we repeat that process several times, and the diagram here shows that we quickly converge to the square root of 2. Now that may look like magic, but it's not. First, it doesn't always work. It doesn't converge, for example, if p is negative, as you would expect. It also doesn't converge if you pick the wrong t. If we had picked t of x equals p over x, the equation t of x equals x would give us the square root of p. However, it doesn't converge. Try it out and you'll see why. You might tinker with this a little bit to get a feel for it. For example, take the problem of finding a cube root or some other root, 17th root or whatever, and see if you can come up with a similar transform that'll do the trick. The next example is a simple pendulum, a simple frictionless pendulum. From physics, we take the example of a rod of length L, which is hinged at the top and carries a weight of mass m. End of the rod makes an angle of theta with the vertical axis. Theta is positive to the right and negative to the left. The equation of motion is theta double prime, that's theta with two derivatives in time, is equal to minus k sine theta, where k is equal to g over L. For initial conditions, we have theta of 0 is equal to theta of sub 0, and theta prime of 0 is equal to 0. Now we're intending to solve this problem numerically 3 different ways. So first, to make clear what we mean by a numerical solution is, instead of continuous functions or smooth functions, we're going to use piecewise linear functions. So integration means the adding of the trapezoidal areas of each one of those segments. Method 1 is something you probably remember from physics. It's a simplification. We note that the sine of x and x are essentially the same thing for small angles. That allows us to substitute for the original equation. Instead, we'll look at theta double prime equals minus k theta with the same initial conditions. Now, the advantage of this is that we can solve it directly. Theta is equal to theta sub 0 times the cosine of t times the square root of k for small t. So the advantage is that we have a complete solution disadvantage is it only holds for small angles. In method 2, we throw away the assumption that the angle is small, so we allow the angle to be anything, and we use an observation that we can simplify the equation by multiplying through by theta prime and noting that we then have exact derivatives. We can integrate directly. We find that theta prime is equal to the square root of 2k times the quantity cosine theta minus cosine theta sub 0. Now, that's nice, but it's not easy. The expression for theta prime looks simple enough, just involving cosine, but you'll find that if you want to solve that, you have to get off into the land of elliptic integrals. We don't want to go there. We want to do something more brute force and direct. And that takes us to method 3. In method 3, we just take the original equation and we simply do a double integration. Now we're doing a numerical integration, so it involves the use of a spreadsheet. This suggested definition of t is that it correspond to that equation. So t of theta is theta sub 0 minus k times the double integral, as shown. And we again approximate the fixed point by doing recursive applications of t. We'll start out with initial data. The function theta 1 of t will be just a straight 1/2 across the board. And then we'll integrate on that basis. Iterate rather, on that basis. The next slide shows a sample from a spreadsheet calculating M3, method 3. Shows time slice on the top, 0, 0.02, etc., etc. It shows the initial guess, theta 0, which is not even close. Then in the next line, the next row rather, we compute minus k sine theta. That's easy enough. The next line, we integrate the first integral. The next line, we do the second integral and finish up by adding in theta sub 0 and multiplying by k. That gives us then theta 2 on the fifth row. Then we simply repeat that over and over again. In our case, we do it 16 times, but do it as many times as you have to get the desired accuracy. The next slide shows an example of how convergence occurs in the method 3. If you look at the different colors, you can see that it shows the initial estimate, the 1/2 across the board, and then it shows different colored lines representing the results of different iterations. You can see that the iterations start out pretty poor. They're not close to the final form. And they very quickly jump together. The 4th, the 8th, the 16th, the 12th iterations are all tightly packed on top of each other. And they agree rather well with the M1 direct computation, the simplification. The next slide shows how M1, M2, and M3 are three methods, how they stack up relative to one another. You can see that both method 2 and method 3 are both tracking method 1 pretty well, but they differ in some details, especially as time gets larger. The next slide shows more data comparing methods 1, 2, and 3. It shows 4 iterations of method 3. It shows method 2 and method 1. That's what the data looks like on the spreadsheet for the higher numbered iterations. Now recall that M1 assumed that the angle was small initially. If we do away with that assumption and take a larger angle, how does M1 compare with M3? For M3, let's take the initial data, the initial angle theta sub 0 to be -3, so it's almost vertical. And let's look at the 1st, the 8th, the 12th, and the 16th iterations on M3. The graph here shows the M3 compared to M1, M1 being in blue, M3 being in violet. You notice that they're not even close to looking the same. You notice that M3 converges kind of slowly. It starts off being flailing, really almost flailing, in that it's nowhere near its ultimate destination. Now the way that we know we're converging graphically is that the iterations overlay each other. So there's no change from iteration to iteration. And the way you can see it on the spreadsheet is just by tracking the numbers, the estimations of theta with respect to time. They'll converge, and numerically they won't change from iteration to iteration. That means that you're done iterating. You found your fixed point. So in conclusion, we've seen a couple of examples of fixed point application. We see that the trick is getting t right in order to get convergence. The spreadsheet work, although we haven't looked into it in detail, if you're familiar with spreadsheets, should be clear that this is not a difficult application. And it should also be clear that the method would be applicable to more complex problems. If instead of a simple pendulum, we take a more compound or complex pendulum with friction and other embellishments, it shouldn't be very hard to adapt this method. I hope you found the topic interesting. Questions and comments are welcome. Other examples are possible if there's an interest. Thanks for listening. This is Wild Red, signing out.